Alright, so suppose we have a surface and somebody's pulling a box on the surface. And just grab a box, so it's really simple. A box, good person pulling on the box as best they can. Okay, so the person is pulling on the box. And suppose the box is already moving 2.4 meters per second. Let's say it's a 60 kilogram box. And they're moving along. Let's say they go 3 meters. And after 3 meters, they are going 5.6 meters per second. So they've gotten faster. And let's say the coefficient of friction between the box and the ground is 0.35. Now what we want to do is we want to see how hard is he actually pulling on the rope. Okay, well there's a couple things going on. He's applying force to the rope, and we also have friction trying to slow him down. We got some distances and speed. So let's just sort of see what we can figure out with what we've got. So I'm going to start simple. I've got my speeds here. I've got a distance. Going back to what we started with the DTV and stuff, let's see if I can use that. So I know he starts at 2.4 and he goes all the way up to 5.6. So if I use my basic V-type stuff, he got faster and faster, and the change in V was 3.2 meters per second. And the average V during this time would be just 4 meters per second. So you just add them up and divide by 2, that's the halfway point. So got 3.2 meters per second faster, and the average V for the entire thing was 4 meters per second. Well, now that I have that, I've got distance, I've got my average V, well I can find my time. So using basic DTV, if I do the 3 meters divided by 4 meters per second, it's only 0.75 seconds. So he's going pretty good here. Alright, well, now that I've got that idea, I can use my time and I can use my delta V to find my acceleration. So the acceleration would be the change in V over change in T. So I'll use my 3.2, I'll divide that by my 0.7, and I will have my acceleration. And that will give me about 4.3 meters per second squared. Okay, now that I have my acceleration, I can actually find something really important. I can find my net force. Okay, so with mass and acceleration, you can always get net force. So my net force is going to be equal to ma. So if I do the 4.3 and I multiply that by the mass of the box, that'll give me around 256 newtons. But that's not how much he is actually pulling with. That's just his net force. That's what he's actually getting to use, because there's also friction involved. So if I find my friction, that's mu Fn, in this case Fn would just come from mg, I can find out how much friction I have. So 0.35 times 60 times 9.81 gives me 206 newtons of friction. Alright, so now I got everything I need. So he's pulling in the box. The first thing he needs to do is he needs to pull with 206 newtons just to cancel out friction, which he does. And then he's pulling with another 256 on top of that yet. That's what his net force is. That's what he's winning with. So if I put those two together and add them up, I can see that his applied force has to be 462 newtons. So he's pulling with 462. 206 of that is being taken away by friction, and the remainder of that is 256 newtons. So now let's change the situation a little bit. Instead of him pulling straight, what if he pulled at an angle? So instead of just pulling straight across, what if instead he pulled this way, let's say at a 25-degree angle, and there's the 462 that we found. What would his acceleration be now? So what is his new acceleration going to be? Well, since he's actually pulling at an angle, he's pulling out this way at 462 newtons, so this way 462 newtons, at 25 degrees. The first thing we need to do is we need to break apart that force into x and y components, the force in the x direction and the force in the y direction. So using my basic trig, I've got a hypotenuse of 462 times the cosine of 25. I can find my force in the x direction, which is about 419 newtons. And this is what's actually being used to try and move the box sideways. Now he's not just pulling sideways, he's also pulling up. So if we find the vertical component, that's 195 newtons. He's pulling up with 195 and to the side with 419. So we've broken apart the force that's at an angle. This part here, this actually goes towards accelerating the box. This one here, since he's pulling up on the box a little bit, he's actually going to reduce the normal force. He's actually putting less pressure on the ground because he's actually pulling up on the box a tiny little bit. So we're going to use this to find our force of friction, because this pulling an angle is going to change our friction. Alright, so if I want my friction, the first thing I need is my Fn. Now when the box was just sitting on the ground, he's pulling sideways, Fn was just my mg. That's right there. But now, since he's pulling up a little bit, we're going to have to subtract what he's pulling up with a little bit. So we'll start with the mg, which is the mass of 60 times gravity, but then we're going to subtract that 195 because he's actually reducing some of the pressure on the ground. So the weight of the box is just under 600 newtons, and then we will subtract 195, which leaves us with around 394 newtons of normal force between the ground and the box. Now that I have my new normal force, I can actually then calculate my new friction. So same coefficient of friction, new Fn. Okay, coefficient of friction was the 0.35. Fn is now 394. So if I multiply those two together, I can get my friction is around 138. So before my friction was 206. Now my friction is only 138 because he's pulling up on the box a little bit, reducing normal force, which in turn reduces friction. This is often why we try and move something heavy. We'll pull up a little bit to try and take care of some of that friction. So now I can try and find my net force the exact same way as before. If I look at what's trying to move the box, that is the 419. It's not the 462. Once you break apart the 462, you're not going to use it again. It's just the force in the x direction. That is the 419. In terms of my slowing force, that is my 138. That's my friction. So if I use those two, I can calculate my net force. I've got 419 trying to move it. I'll subtract the 138 for friction. 419 take away 138, net force around 281 newtons. Now that I have the net force, I can find my accelerations. Acceleration would be the net force divided by the mass. So the mass hasn't changed. So we have an acceleration now of about 4.7 meters per second squared.